This is a video screencast for lab number 7, the Archimedes Principle Lab. And let's first review a little bit about Archimedes Principle. So, in a fluid, the pressure increases with depth. And one can understand that by looking at two different depths in a fluid. And the lower depth has more fluid above it, and the weight of that fluid generates a greater pressure. Now, if you put an object in a fluid, because of that pressure difference, the force on the bottom of the object, because it's lower in the fluid, will be greater than the force on the top of the object, because the top of the object is higher up in the fluid. That difference in the force on the bottom and the top results in a net upward force that we call the buoyant force. Now, Archimedes deduced that the buoyant force is equal to the weight of the fluid displaced by the submerged object. In symbol form, the buoyant force is mass times g, the mass of the fluid displaced times g. We can rewrite Archimedes' principle in terms of density by rewriting mass as density times volume, and then Archimedes' principle can be written as the density of the fluid, the volume displaced by the object, times g. Now, the lab today is to verify Archimedes' principle, and the prediction of Archimedes' principle can be done by measuring the volume of the object. When you know the volume of the object, you can predict the buoyant force on the object when it's submerged. And the way that the volume can be determined, one way to determine the volume of an object is to put it into some water and measure the difference in the volume in the water. And the data table for that part of the lab involves measuring the water levels before and after the objects are submerged. Now, in the lab, there are three different metal cylinders that are used to test Archimedes' principle: a copper and a tin and a zinc. And we're just going to give you the values of the water levels, and you will complete the remainder of the data table. Now, for the copper cylinder, the volume of the water before the cylinder was placed in the water was 62, and then afterwards 69. For the tin, it was 62 before, 66 after, and the zinc 62 before and 68 after. Now, you're to complete the remaining entries in the data table. I'll just go over those columns. So the volume of the cylinder, as we've discussed, is going to be the difference between the two water levels. The next column is converting the volume measurement into cubic meters. Now, the graduated cylinders that measure the water volume is in milliliters, and you need to convert to cubic meters, and you need a conversion factor, and you need to know that, well, a milliliter is a cubic centimeter, and then converting a cubic centimeter to a cubic meter involves the conversion factor that a cubic centimeter is 1/1,000,000th of a cubic meter, which in scientific notation, that's 1 times 10 to the minus 6. So essentially, converting from milliliters to cubic meters is multiplying by 1 times 10 to the minus 6, which is moving 6 decimal places to the left. And then the final column in that data table is the predicted buoyant force, which is Archimedes' principle. The buoyant force is the density of the fluid. In this case, it's water, which has a density of 1,000 kilograms per cubic meters, times the volume of the object, which is what you calculated in the previous column, and then g, multiplying by g, the acceleration due to gravity, 9.8 meters per second squared. Now, the second part of the lab and the second data table is experimentally measuring the buoyant force, and that can be done in the following way: is hanging an object on a scale and recording the mass, and then putting the object in water, and the scale reading will be less. The mass hasn't really changed, but because of the buoyant force, the scale will actually read a smaller value. And the difference in those two weights, the mass times g, is the buoyant force. So the difference between the weight in air and the weight in water will be the experimental measurement of the buoyant force. Now the data table contains the measurements of those masses, and we're just going to give you those values. So for the copper cylinder, the mass in the air was 0.0624 kilograms, the mass in water 0.0552, for the tin 0.0292, in air, and in water 0.0250, and then finally the zinc 0.0426 in air and 0.0369 in water. Now you're to complete the remaining entries in the data table. The weight column is just calculating the weight mass times g. The apparent weight is taking the mass in water and multiplying by g. The buoyant force, the experimental buoyant force, as we already discussed, is the difference between the weight in air and the weight in water. And then the final column is comparing your buoyant force from Table 1 and the buoyant force in Table 2. Percentage difference is, the general formula for percentage difference, x1 minus x2 over x1 plus x2 over 2. In this case, you're comparing the buoyant force from Table 1, that'll be your x1, and then the buoyant force from Table 2, that'll be your x2. And then finally answering the question, did your data support the validity of Archimedes' principle? Did you verify Archimedes' principle? That completes this screencast.